Okay, we have a question here involving a right triangle. They're talking about a triangle where the hypotenuse is locked in at 64, so it could be a tall, skinny one like this, a kind of balanced one like this, a low, flat one like this, but always 64 on the long side. The vertical and horizontal sides, which I've called y and x, are changing, so the triangle's kind of morphing from this to this to this as we watch the y getting shorter all the time. They say the vertical leg, so y, is getting shorter by 5 centimeters per second, which we would write dy dt equals minus 5. At what rate is the angle opposite the vertical side, the one I've marked theta here, changing when the horizontal side, x, is 40 centimeters long? So we need some kind of expression that includes this angle, and we know that the y side is changing, so we want to include that also. When I first looked at this, the first thing I thought of was to use tangent. I don't remember precisely why I picked that, but it wasn't a good choice, and here's why. If you write that equation, you get, sorry, not sine, you get tangent theta equals y over x. And then when I went to differentiate this, it turned into a bit of a hairball because it had three variables in it. It's got the angle, it's got y, which is changing, and x, which is also changing. So that worked out not too well. I am going to try it now using a different trig function, and I'm thinking it might be beneficial to avoid having the three variables by using this 64. If I do opposite over hypotenuse, if I use the sine function, I get sine theta equals opposite over hypotenuse. And I think this might do the job and not produce as such a hairy derivative. When we differentiate this, the derivative of sine theta is cosine theta d theta. On this side, we have y to the first power, so we multiply by 1, we get y to the 0th power. This ends up just being 1 over 64, y to the 0, which I don't intend to write, and dy. And then we divide both sides by dt. And ta-da, there's a rate equation that we should be able to use. If we're going to use this, they say we need cosine theta, so we need this angle, which we don't have. That's a bit of a problem. Guess what? Time for one of those side calculations that seems to happen every single time. We're told in our triangle that this x value, at the instant that we're interested, is 40 centimeters. So we have 40 there, which means in this triangle we have adjacent and hypotenuse are 40 and 64. So off to the side, I'm going to put cosine theta equals adjacent over hypotenuse. If we do 40 divided by 64 equals inverse cosine, I find that that angle is 51.3 degrees. You can do it in radians if you want, but I think this will be okay. So for our cosine theta, we're doing cosine 51.3 degrees. You can use that angle and put your calculator in degree mode, or you can find that angle in rads, whatever it is, and keep your calculator in radian mode. It's all good. D theta dt is what we're supposed to find. At what rate is the angle changing? So for now, that remains unknown. On this side, we have 1/64th, and dy dt, they told us, is minus 5. The y side is shrinking that fast. So if we want d theta dt, it's got to be 1/16th times negative 5 divided by this cosine, which I'm going to hammer out right now. 1/16th times negative 5 divided by 51.3 cosine. And I get d theta dt is pretty much exactly, I get 0.4998, so basically negative 0.5. And the units for this, now this is a little tricky. When you get an angle rate out of a calculus formula, It's pretty much always in radians per second. It's angle units divided by time units, so radians per second. You might be thinking, you were just working in degrees, how come you're suddenly saying that everything has to be in radians? It doesn't matter what form you put an angle into a calculator if you were using it inside a trig function. If you're doing sine or cosine or tangent of something, then you can use either degrees or radians as long as your calculator's in the appropriate mode. But when a number comes out of a formula like this, it will always be in radians unless you go out of your way to convert it. So d theta dt is minus half a radian per second. That would mean that the angle is shrinking, which actually, I was going to say that's surprising, but it's not. I take that back. As this side gets shorter, the angle across from it has to shrink. So it is appropriate and unsurprising for that to come out negative. It means we're losing degrees here because our opposite side is shrinking.